They're smaller than a city, denser than an atomic nucleus, and they might exist right now hidden in the dark. Quark stars, the theoretical monsters beyond neutron stars. What could possibly survive inside something so extreme? Stay tuned as we explore this cosmic mystery. If you enjoy it, please like, subscribe, and share, and tell us in the comments, do you think quark stars really exist? Thank you for watching. Now let's begin. In the vast life cycle of stars, every phase is governed by balance. A star endures as long as the outward push of fusion can resist the inward pull of gravity. Deep within its core, hydrogen nuclei merge to form helium, releasing energy that radiates outward as light and heat. This pressure counteracts the star's own immense weight, keeping it stable through millions or even billions of years. But this equilibrium is temporary. Eventually the fuel runs out. The heavier the star, the faster it burns through its reserves, and when the final layers of fusion fade, the internal furnace goes dark. What follows is collapse swift and absolute. Gravity, the same force that held the star together, now pulls it inward without opposition. The outer layers fall toward the center, accelerating as they go. The matter becomes denser with each passing moment, and the core compresses under pressures that exceed imagination. Temperatures climb to hundreds of billions of degrees Celsius, yet no new form of fusion can resist the crushing weight. At these scales, even atomic nuclei are strained beyond endurance. In stars several times more massive than the Sun, this collapse ends not with silence but with explosion. The implosion rebounds as a supernova, a brief but brilliant outburst that can outshine entire galaxies. For a few days or weeks, the star's light floods across space, carrying with it the elements forged in its violent interior carbon-oxygen ion, and all the materials that will one day form planets and life. When the outer layers are expelled, what remains is the core, a dense remnant of unimaginable compactness. If the star is small enough, that remnant becomes a white dwarf held up by electron pressure. But for larger stars, the collapse continues past that limit. Electrons and protons are forced together, forming neutrons, and the matter becomes so dense that a teaspoon of it would weigh billions of tons. The result is a neutron star, a compact sphere only about 20 kilometers across, yet more massive than the Sun. Here atomic structure breaks down entirely. The neutrons, bound together by the strong nuclear force, press against one another so tightly that they form a continuous medium. In this state, matter behaves like a single immense nucleus, supported only by the degeneracy pressure of neutrons. The surface of such a star is a paradox, solid, yet fluid, dense yet fragile. Gravity there is so strong that anything falling onto it strikes at nearly the speed of light, releasing bursts of X-rays or gamma rays. For the observer, the neutron star is an invisible ember unless it spins rapidly and emits beams of radiation as seen in pulsars. Each rotation produces a rhythmic flash like a distant cosmic heartbeat. Beneath that flickering signal lies the record of stellar death, a reminder of how ordinary matter can be pressed into extraordinary form. The process of reaching this state is governed entirely by gravity and quantum physics. No chemical or biological process compares to it. As the core collapses, the electrons are captured by protons, producing neutrons and neutrinos in immense numbers. The neutrinos escape into space, carrying away most of the energy of collapse. What remains is a core of neutrons locked in equilibrium between gravitational pull and nuclear repulsion. This is the boundary where conventional physics remains functional but strained. The equations describing the neutron star depend on the balance between gravity and the strong force, and though they succeed in reproducing many observed properties, they may not hold indefinitely. When the mass of the collapsing core exceeds roughly twice that of the Sun, even neutron pressure may no longer suffice. The star teeters on the brink of another transformation, where the forces holding neutrons together may yield to a deeper breakdown of structure. Beyond this point lies speculation, but also possibility, the region where quark matter might emerge. The existence of neutron stars shows how nature approaches the extreme limits of matter. They are laboratories of physics under conditions that cannot be recreated on Earth. Their surfaces mark the transition between nuclear density and the vacuum of space, a contrast so severe that space-time itself curves visibly. The magnetic fields surrounding them are billions of times stronger than those produced in any human experiment. Their rotation can exceed hundreds of times per second, yet their structure remains intact. All these properties confirm that neutron stars are real, observable, and testable. But they also point toward limits thresholds where known matter might fail to resist further compression. In that failure may lie the clue to what follows. The story of stellar death does not always end with a black hole. Between the certainty of neutron matter and the finality of singularity may exist another phase, more compact, more exotic, and still unseen. Theoretical models predict that in some of the heaviest neutron stars the central density could surpass the level at which quarks, the fundamental components of neutrons and protons, are no longer confined within individual particles. This threshold is called deconfinement. If reached, it could produce a core made not of neutrons but of free quarks, forming what physicists call quark matter. In such a scenario, the familiar boundaries of atomic structure dissolve, and matter transitions to a state described not by nuclear physics, but by quantum chromodynamics, the theory of the strong interaction. Yet for now, this remains theoretical. No telescope has directly seen a quark star. No pulse or spectrum has revealed one unambiguously. Still, the physics of collapse naturally raises the question, what happens beyond the neutron star limit? The boundary between neutron matter and quark matter is not just a curiosity. It is a frontier where the laws of nature are tested under extremes of density, gravity, and temperature. The stars that reach this point mark the meeting place between observation and theory, between what is seen and what is inferred. To understand quark stars, one must first follow the path of collapse to its end, the moment when fusion ceases, gravity takes over, and the ordinary materials of the cosmos are pressed into forms that strain every known equation. In the silence that follows, a supernova, amid the debris of the star that lies the beginning of a deeper inquiry. The light has faded, but the matter remains dense beyond comprehension, marking the first step toward understanding the hypothetical world beyond neutron stars. A neutron star stands as one of the most compact and enduring objects in the universe, born from the implosion of a once luminous giant. It embodies the last stable form of matter, known to exist before collapse yields to a black hole. Its structure, though invisible to the naked eye, is described with precision by physics that balances two immense forces, the relentless inward pull of gravity and the outward push of neutron degeneracy pressure. This balance defines the narrow boundary between existence and implosion. Within this object, the familiar hierarchy of matter vanishes. Atoms which normally contain vast spaces between nuclei and electrons are crushed until those spaces no longer exist. The nuclei themselves merge into a continuous field of neutrons packed so tightly that a single teaspoon of the material would outweigh entire mountains. The matter behaves like a superfluid, an exotic state, where particles move without friction, flowing collectively as if the entire interior were one entity. Such a fluid cannot be produced on Earth except for tiny glimpses inside laboratories that chill atoms to near absolute zero. Yet inside a neutron star, this fluid exists under temperatures of millions of degrees Celsius, constrained by gravity that is billions of times stronger than Earth's. The surface of a neutron star is a boundary of contradictions. It may appear smooth, yet the crust beneath is crystalline, made of compressed nuclei, locked in patterns that no solid on Earth can replicate. Beneath this crust lies the inner mantle, where neutrons drip from atomic clusters and form dense liquid layers. Further inward, the density rises beyond that of an atomic nucleus. Here, the behavior of matter is determined not by chemistry, but by quantum chromodynamics, the theory that describes how quarks interact through the strong nuclear force. This region marks the approach toward deconfinement, though in most neutron stars it remains unbroken. The magnetic fields at the surface are intense beyond any terrestrial comparison. They twist and arc, channeling charged particles into beams that sweep through space. When such a star spins rapidly, these beams produce pulses detectable as radio or X-ray emissions. Astronomers call these objects pulsars. Their rotation periods range from seconds to fractions of a millisecond, yet the timing of their signals is so precise that they rival atomic clocks. Each pulse is a reminder of the star's perfect stability, a body so dense and compact that it resists deformation even while spinning hundreds of times per second. Observations of pulsars have given scientists a window into the physics of extreme matter. By measuring their rotation brightness and slow decay, one can infer the internal stiffness of neutron-rich material known as the equation of state. This equation links pressure, density, and temperature, providing a framework to predict how matter behaves inside such stars. Yet as accurate as these models have become, they reveal a limit. The equation of state cannot be arbitrarily stiff. It cannot resist gravity indefinitely. As the mass of a neutron star increases, its core density grows until neutrons themselves may begin to merge or dissolve. At roughly twice the mass of the Sun, theory predicts that degeneracy pressure may fail. Beyond that limit, the star must either collapse into a black hole or transition into a state of matter even denser than neutrons alone. The interior of a massive neutron star is a mystery that remains partly hidden from observation. Astronomers measure its mass by tracking companion stars in binary systems and estimate its radius from X-ray emissions, but both quantities are notoriously difficult to constrain. Small changes in radius can reveal large changes in internal structure, and these details remain uncertain. Some measurements suggest that certain neutron stars approach the limit where deconfinement could begin, implying that their cores may contain quark matter. Yet none of these observations are definitive. The difference between an ordinary neutron star and a hypothetical hybrid one with a quark core is subtle, detectable only through precise modeling of cooling rates, spin-down behavior, and gravitational wave signals during mergers. The complexity of neutron stars extends beyond their mass and radius. Their internal layers contain superfluid neutrons and superconducting protons that together create a delicate network of vortices and magnetic flux tubes. These structures determine how the star spins and how it gradually loses energy. Occasionally, a neutron star experiences a sudden change in its rotation rate, a glitch caused by a rearrangement within its superfluid interior. Such events reveal the hidden dynamics of the matter within, offering indirect evidence of the extreme physical laws that govern it. Every neutron star represents the endpoint of nuclear matter, where protons and neutrons exist as tightly bound entities under constant compression. The boundary between the crust and the core is smooth in density but sharp in physics. The crust behaves like a solid lattice, while the core is a liquid of interacting neutrons and a small fraction of protons and electrons. Deeper still, under enough pressure, these components may reorganize into more exotic particles, such as hyperons, which contain strange quarks. The presence of such particles softens the equation of state, allowing the star to compact further. Whether these particles exist in reality remains uncertain, yet their inclusion in theoretical models shows how close neutron stars are to the edge of another phase of matter. As observational instruments improve from radio arrays to gravitational wave detectors, the understanding of neutron stars sharpens. Each new observation challenges the boundaries of theory, pressing scientists to reconcile measurements with predictions. Some stars, such as the unusually heavy pulsars found in binary systems, already seem too massive for certain models of neutron matter to support. If confirmed, these could represent transitional objects massive enough to question the sufficiency of neutron pressure, but not yet collapsed into black holes. These observations define the frontier of modern astrophysics, a domain where the known laws of nuclear physics are tested under cosmic compression. Within these dense remnants, time slows light bends and ordinary matter ceases to resemble its familiar form. Yet even in their stillness, neutron stars are dynamic in their influence. Their gravitational pull shapes the orbits of companions, their magnetic fields sculpt space around them, and their radiation marks them as beacons across galaxies. They demonstrate how the universe can create order from chaos through the precise balance of fundamental forces. And still, they raise a question that lingers at the edge of understanding: what happens when even neutron pressure cannot hold. At that unseen threshold, matter may undergo its final transformation. The neutrons themselves may dissolve into a sea of quarks, leading to a new form of compact object that no telescope has yet confirmed, but that theory continues to predict. To approach that possibility, one must first understand how neutron stars push matter to its ultimate limit, how gravity and the strong force reach equilibrium for the final time before giving way to a deeper state of existence. As the mass of a neutron star increases, the equilibrium that defines its existence begins to narrow. Every additional fraction of solar mass brings the interior closer to an invisible boundary, where the known states of matter may no longer endure. This boundary is not a line one can draw or see. It is a threshold defined by pressure density and the laws of quantum mechanics under gravity's absolute command. Inside these massive remnants, the compression continues long after the outer layers have stabilized. The neutrons already crowded beyond the densities of atomic nuclei are pressed even closer together. The strong nuclear force which repels at very short distances resists this compression, but gravity remains relentless. The struggle between these forces defines the last stand of nuclear matter. Physicists call this region the approach to degeneracy, a domain where the Pauli exclusion principle, the rule that prevents identical fermions from occupying the same quantum state, becomes the only thing keeping the star from collapsing further. In ordinary conditions, degeneracy pressure is sufficient to hold up white dwarfs against gravity. In neutron stars, it is the degeneracy of neutrons that provides this resistance. But as mass increases, the available quantum states become saturated, and the pressure that arises from exclusion alone can no longer balance the inward force. At this stage, the density inside the core exceeds several times that of a typical atomic nucleus. Theoretical models describe these conditions in terms of the equation of state, a mathematical relationship between pressure and energy density. The exact form of this equation determines whether a given mass of neutron matter can remain stable or must collapse. For low-mass neutron stars, the equation is relatively well constrained by laboratory nuclear physics and astrophysical observation. For massive ones, however, it enters an uncertain regime. The behavior of matter under such pressure is not something that can be tested directly. The densities involved are too high to reproduce, and the interactions between neutrons and their quark constituents remain too complex to simulate perfectly. What can be said is that as this threshold is approached, the structure of the star changes subtly. Its radius begins to shrink more rapidly with each small increase in mass. The crust becomes thinner, the outer layers more compact, and the gravitational redshift more pronounced. The light escaping from the surface is stretched into longer wavelengths, and time itself passes more slowly in the star's gravitational field. For an observer far away, the pulses from such an object appear slightly delayed each tick of the star's rotation, warped by the curvature of space-time. Yet even under these distortions, the neutron star holds. It is still a physical object, its matter still confined, though only barely. To visualize this state is to imagine matter stripped of all its familiar structure. There are no atoms, no separate nuclei, no gaps between particles. Instead, there exists a continuous fluid of neutrons with a small admixture of protons and electrons to maintain charge balance. The neutrons behave collectively, their individual identities blurred by the closeness of their wave functions. Quantum mechanics describes them as overlapping fields occupying an enormous number of momentum states. Each neutron's energy contributes to the total pressure, and the sum of all these energies defines the star's stability. When mass and density rise high enough, the chemical potential of neutrons, the energy required to add one more, becomes so great that it rivals the energy scale associated with quark confinement. This is where deconfinement begins to loom as a possibility. The neutrons may cease to exist as discrete particles dissolving into their constituent quarks. This transformation, if it occurs, does not happen uniformly or explosively. It begins in the core at the deepest and most compressed region of the star where the gravitational potential is highest. There the matter may first enter a mixed phase, part neutron, part quark, a gradual blending of two states. Outside this core, the layers remain neutron-rich, unchanged for the moment, maintaining the overall stability of the object. The challenge for astrophysics is that this process, though central to theory, leaves almost no direct signature. From the surface, a neutron star with an emerging quark core would look nearly identical to one without. The gravitational pull, the radiation and the pulse timing each would differ only slightly within the margin of observational error. Yet these minute differences are what scientists search for, hoping to find evidence that nature indeed crosses this threshold. The boundary of degeneracy represents one of the sharpest frontiers in modern physics. It is the point where the theories of nuclear matter tested in particle accelerators and laboratories merge with general relativity, which governs gravity and space-time. Each theory alone is well established, but together they produce conditions so extreme that neither can be applied with full confidence. The structure of a massive neutron star thus becomes an experiment written in the cosmos, revealing how nature resolves the tension between quantum exclusion and gravitational collapse. Theoretical research divides these stars into categories based on mass and internal composition. Below a certain limit, neutron stars remain entirely stable, their interiors dominated by neutron matter. Slightly above that, they may become hybrid stars where a quark core coexists with a neutron envelope. Beyond that lies the regime of total deconfinement, where the star could exist as a pure quark star composed entirely of up, down, and possibly strange quarks. Whether any real object ever crosses these boundaries remains unproven, but the equations predict that such transitions are physically possible. As mass increases toward the critical limit, the gravitational field also strengthens, curving space around the star to an extreme degree. The escape velocity approaches the speed of light. Photons emitted from the surface lose much of their energy before reaching open space, making the object appear dimmer than its temperature would suggest. The interior pressure rises until it is measured in tens of trillions of pascals, and the density exceeds that of a nucleus by an order of magnitude. These numbers stretch imagination, yet they remain within the framework of physical law. The degeneracy pressure, though, weakened, still acts. The strong nuclear force still binds the neutrons together, delaying their dissolution. The result is a star balanced on the knife edge of collapse, its fate determined by fractions of mass and the details of interactions too complex to measure directly. Such stars are rare but crucial to understanding the transition between matter as it is known and matter as it might become. Each discovery of a heavier neutron star extends the upper limit of stability, redefining where the boundary of degeneracy may lie. As observational data accumulates from pulsar timing, from X-ray spectra, from gravitational wave mergers, the models refine, approaching a consensus that this limit may exist near 2 to 2.5 solar masses. Beyond it, neutron degeneracy alone cannot hold, and something new must emerge. Whether that something is collapse into a black hole or the birth of a quark star remains one of the most profound open questions in astrophysics. For now, neutron stars at this edge continue to spin pulse and cool, marking the quiet border between certainty and speculation. They are the last survivors before the unknown. At the heart of the most massive neutron stars, the pressure may reach a threshold where the structure of matter itself begins to change. Here the familiar picture of neutrons and protons nucleons bound by the strong force ceases to describe reality accurately. The density becomes so immense that the individual boundaries of these particles overlap, and their internal components, the quarks, start to move freely within a shared medium. This process, known as deconfinement, marks one of the deepest transitions in the universe. Under normal conditions, quarks never exist in isolation. They're confined within protons and neutrons by the strong force, which grows stronger as quarks attempt to separate. This principle, called color confinement, ensures that all observable matter consists of color-neutral combinations of quarks bound tightly together. The energy required to pull two quarks apart is so large that it would create new quark-antiquark pairs before isolation could occur. But in the extreme pressure of a neutron star's core, the distance between nucleons shrinks until confinement loses its meaning. The quarks no longer belong to individual particles, but instead form a continuous medium, a plasma of up-down and possibly strange quarks. In laboratories on Earth, this state of matter has been glimpsed briefly in high-energy collisions within particle accelerators. When heavy ions collide at near light speed, they create fleeting droplets of quark-gluon plasma that last only trillionths of a second before cooling and recombining into ordinary matter. These experiments confirm that under sufficient temperature and energy density, confinement can break. Yet the environment inside a neutron star is entirely different. There the temperature is comparatively low, but the pressure is unimaginably high. It is not heat but compression that drives deconfinement. The strong force which resists separation of quarks must also respond to their forced proximity. The result is a change in the internal symmetry of matter, a rearrangement of its fundamental components into a collective state described by quantum chromodynamics, or QCD. This theory predicts that under such conditions, quarks interact through the exchange of gluons, the carriers of the strong force, in a way that allows them to move collectively while remaining bound within the overall mass of the star. The appearance of quark matter is not expected to occur abruptly. Instead, it likely begins with a mixed phase in the center, where pockets of deconfined quarks coexist with compressed nuclear matter. This gradual transition reflects the balance between energy and pressure. As density increases, the cost of maintaining nucleon identity exceeds the energy required to free the quarks. Beyond a critical density, the entire core may transform into a quark-gluon medium, forming what theorists call a quark core. The outer layers remain composed of neutron matter, creating a structure that is stable but profoundly altered. In this interior, the rules of matter change. The pressure is no longer governed by the interactions between neutrons, but by the dynamics of quarks and gluons. The energy density rises, but so does the stiffness of the equation of state, allowing the star to resist further collapse. In some theoretical models, this new form of matter can support additional mass, meaning that a star containing a quark core could exist in equilibrium where a purely neutron star would fail. This possibility suggests that nature might permit a class of hybrid stars objects with quark centers and nuclear exteriors occupying the boundary between the known and the speculative. The concept of deconfinement challenges not only nuclear physics but also astrophysics as a whole. It connects phenomena across scales from the interiors of atomic nuclei to the dynamics of entire stars. Each neutron or proton in ordinary matter is a miniature confinement zone, yet in the crushed cores of massive remnants, these zones merge, producing a collective state that reflects the universe's most fundamental interactions. The quarks themselves come in three varieties or flavors: up, down, and strange. The first two are the building blocks of protons and neutrons, while the third, the strange quark, appears only in extreme environments. The presence of strange quarks may lower the energy of the deconfined phase, making it more stable under compression. If strange quarks are produced in sufficient numbers, the matter becomes what physicists call strange quark matter, a hypothetical state that could remain stable even outside a star, though no evidence for such stability exists. This idea forms the foundation of later models proposing strange stars in which deconfined quark matter dominates entirely. The existence of deconfinement inside real neutron stars remains unconfirmed, yet several observations hint that something unusual may be happening. The detection of unusually massive neutron stars near or above two solar masses suggests that their interiors might contain matter stiffer than expected from standard nuclear equations. Similarly, gravitational wave signals from neutron star mergers provide clues about how such dense matter behaves under compression. Subtle differences in the way stars deform and radiate before merging could reveal the presence of quark matter, but current measurements remain too uncertain to draw firm conclusions. The theoretical boundary between confinement and deconfinement depends sensitively on the details of QCD, which cannot yet be solved exactly in this regime. Instead, scientists rely on approximate models, numerical simulations, and comparisons to experimental data from particle colliders. These approaches suggest that the transition could occur at densities between 2 and 5 times the nuclear saturation density corresponding to the conditions near the cores of the heaviest neutron stars known. Beyond these densities, matter may flow more freely, quarks forming a fluid governed by collective color interactions rather than individual nuclear bonds. The temperature inside such a core would still be millions of degrees, but this is cold by the standards of particle physics. What dominates here is the pressure, trillions of pascals, and the immense gravitational confinement. In this environment, energy and mass become indistinguishable, and the curvature of space-time couples directly to the behavior of quarks themselves. The study of deconfinement bridges quantum theory and general relativity, two frameworks that rarely meet in a single physical system. The core of a massive neutron star may be one of the few places where both operate simultaneously with measurable consequences. The existence of such a region would mean that the most basic components of matter can behave collectively to shape the structure of an entire star. Yet for all its theoretical elegance, deconfinement remains hidden from direct observation. No signal has yet confirmed it. No pulse or spectrum has announced its presence. Its existence must be inferred through indirect evidence, through how a star cools, how it spins down, or how it responds to tidal forces during a merger. Each of these subtle behaviors encodes the physics of its interior, waiting to be read with instruments sensitive enough to detect the difference between neutrons bound and quarks freed. For now, deconfinement remains a frontier, a transformation that exists in the equations and in the extremes of nature, unseen, but consistent with the laws that govern both the smallest particles and the largest stars. In that hidden depth, the very identity of matter may dissolve, giving rise to a form of existence beyond the reach of current understanding, a state that is neither nuclear nor singular, but something in between, sustained by gravity and defined by the release of the quarks themselves. The emergence of quark matter brings the study of the universe to its most fundamental scale, where the forces shaping atoms, stars, and galaxies converge in a single system. At this depth, gravity compresses matter so completely that the strong nuclear force, which normally acts only within atomic nuclei, becomes the dominant architect of an entire star. This force, carried by particles called gluons, binds quarks together through what physicists describe as color charge, a property unrelated to visible color but essential to quantum chromodynamics, the theory of the strong interaction. In ordinary matter, gluons hold quarks in confined groups of three forming protons and neutrons. These particles in turn assemble into atomic nuclei, giving rise to the structure of matter throughout the cosmos. Inside a quark star or a quark core, this organization disappears. The gluon fields extend throughout the interior, weaving an unbroken network that connects every quark to every other. Instead of being trapped inside individual particles, quarks move freely within this collective field, exchanging color charge continually. The result is a fluid that is both bound and unconfined, a state where the energy of the strong force permeates every cubic centimeter of space. The strength of this force is immense. Unlike gravity, which weakens with distance, the strong force intensifies as quarks attempt to separate. But when they are forced closer than the confinement scale, the effective interaction becomes weaker, a phenomenon known as asymptotic freedom. This means that at the enormous densities of a quark star's core, quarks may move almost independently, interacting only through residual effects of the gluon field. The equations describing this behavior arise from quantum chromodynamics, one of the most successful yet mathematically intricate theories in physics. It explains how quarks, which come in three flavors up-down and strange in three colors red, green, and blue, combine to form color-neutral configurations. In the deconfined state, these distinctions remain, but they manifest as patterns in the distribution of energy rather than as separate particles. Every quark carries both mass and kinetic energy, contributing to the total pressure that resists further collapse. The balance between gravitational attraction and quark pressure defines whether a quark star can exist in stable form. Within this framework, the strong force determines not just the binding of quarks, but also the stiffness of the equation of state, the relation between pressure and density that governs the structure of the star. If quark interactions produce a stiff equation of state, the star can support greater mass without collapsing into a black hole. If the equation is soft, the object becomes unstable and succumbs to gravity. Determining which of these possibilities nature prefers remains one of the central challenges in astrophysics. Quark matter, if real, may also display exotic phases. Under high density and low temperature, theoretical models predict that quarks could form Cooper pairs-bound states, analogous to the electron pairs in superconductors. This phase, called color superconductivity, would alter how the star conducts heat, carries magnetic fields, and emits radiation. In this state, the quarks form pairs that condense into a coherent quantum fluid, reducing resistance to motion and possibly locking magnetic flux into stable patterns. The internal structure of such a star would then depend not only on density, but on the symmetry of the paired quarks. Some models describe color-flavor-locked matter, in which up-down and strange quarks pair across all colors, producing a perfectly symmetric phase that is exceptionally stable. If this phase exists, it could define the deepest interior of a quark star invisible, yet shaping its behavior. These conditions, though extreme, follow from established physical principles. The strong force is known to dominate interactions at subatomic scales, and its behavior at high density is well described by quantum chromodynamics. The difficulty lies not in the theory itself, but in its application. The equations are too complex to solve, exactly under the pressures of a compact star. Physicists rely on approximations such as perturbative expansions and lattice QCD simulations, but these methods struggle at the densities where quark matter might exist. As a result, the precise relationship between pressure, density, and energy remains uncertain. This uncertainty translates directly into uncertainty about whether quark stars can exist at all. Theoretical work suggests that quark matter could be more stable than nuclear matter under some conditions, particularly when strange quarks are included. Strange quark matter might have lower energy per particle, allowing it to remain bound even without external pressure. If so, any neutron star that reached deconfinement might naturally evolve into a quark star. Conversely, if quark matter is less stable, it would exist only transiently, collapsing further into a black hole. The answer depends on the fine balance of quantum effects deep inside the matter, far beyond current experimental reach. Despite these challenges, hints of quark matter continue to appear indirectly in astrophysical data. Observations of compact stars near the maximum known mass suggest that their cores must be supported by something beyond simple neutron degeneracy. Gravitational wave detections from mergers reveal how these stars deform under tidal stress, and some signals appear slightly softer than predicted for pure neutron matter. These discrepancies could hint at the presence of quark phases within, though alternative explanations remain plausible. The strength of the strong force means that even minor variations in density can produce major changes in structure. The entire interior of a quark star would be a single continuous medium of immense energy density. The pressure at its center could exceed 100 trillion pascals, enough to alter the geometry of spacetime around it. Gravity would curve the paths of light so strongly that any photons escaping from the surface would be redshifted beyond visible wavelengths. The surface itself might not be solid or gaseous, but a thin transition layer where quark matter meets vacuum. In this boundary, quarks recombine briefly into ordinary hadrons before disintegrating again, creating a narrow region of intense particle flux. From a distance, such a star might appear faint and featureless, its radiation dominated by thermal emission at X-ray energies. The magnetic fields threading through this plasma would be extraordinary, potentially strong enough to influence the alignment of quark spins and alter the pairing structure. The interplay between these magnetic fields and the quark fluid remains an open field of research. If color superconductivity occurs, it could partially screen or reorganize magnetic flux, giving rise to patterns unlike those seen in neutron stars. Understanding such mechanisms requires connecting quantum theory to astrophysical magnetism a task at the frontier of modern physics. The strong force thus plays two roles in the story of quark matter. It binds quarks so powerfully that they cannot be separated under ordinary conditions, yet it also permits their collective freedom when compressed to extreme density. In doing so, it defines the possible existence of quark stars objects that bridge the gap between nuclear matter and gravitational collapse. These hypothetical stars are not simply denser versions of neutron stars, but entirely new states of matter governed by principles that operate both at the scale of quarks and across kilometers of stellar interior. Each theoretical model extends the reach of quantum chromodynamics beyond the laboratory, suggesting that the same force that binds the smallest particles might also support one of the largest coherent objects in the universe. Until observations confirm or refute their existence, quark stars remain both a challenge and a promise, a natural experiment written in the fabric of matter, itself shaped by the strongest force known and hidden behind the quiet surfaces of collapsed stars. Among the many possibilities that arise from the study of dense matter, one stands apart for its elegance and its potential to rewrite the understanding of stability in the universe. This is the strange quark matter hypothesis, the idea that a mixture of up-down and strange quarks could form a stable phase of matter, more fundamental and enduring than the nuclear matter composing atoms and stars. In ordinary matter, up and down quarks dominate confined within protons and neutrons. Strange quarks, heavier and less common, appear fleetingly in high-energy collisions, or within certain unstable particles. But if conditions become sufficiently dense as they may in the cores of massive neutron stars, strange quarks could appear in significant numbers. Their introduction alters the balance of forces and energies that govern matter's behavior. In quantum chromodynamics, each quark flavor contributes to the total energy of the system through both its mass and its interactions. When strange quarks enter the mix, the overall energy per baryon may decrease, potentially making the resulting state more stable than neutron matter. If this occurs, the material would not rely on external pressure to exist. It could remain bound even if removed from the star. This possibility forms the foundation of the strange quark matter hypothesis. First proposed in the late 20th century, it suggests that the true ground state of matter, the most stable form possible under the strong force, might not be iron nuclei as long assumed, but rather a uniform sea of up-down and strange quarks. If correct, this would mean that ordinary matter is only metastable existing as it does, because conditions in the early universe prevented the formation of strange matter on large scales. In theory, a single droplet of strange matter, if ever created, could convert surrounding nuclear material into more of itself by absorbing nucleons and releasing energy. Such an idea is dramatic, but it remains untested and highly uncertain. The formation of strange quark matter depends sensitively on the energy balance among quark flavors, the strength of the strong coupling constant, and the effects of quantum confinement at high density. None of these quantities are known precisely under the conditions that exist in a compact star. Laboratory experiments have produced quark-gluon plasma at high temperature, but not at the low temperature and immense pressure required for strange quark matter. For now it remains an elegant theoretical possibility rather than an observed reality. The introduction of strange quarks changes the microphysics of the star in profound ways. The presence of a third quark flavor allows charge neutrality to be achieved with fewer electrons, reducing the overall energy of the system. The resulting matter would behave as a degenerate Fermi gas of quarks, potentially exhibiting color superconductivity, where quarks form pairs across colors and flavors. This phase, called the color-flavor locked state, would be perfectly symmetric, with each quark type participating equally in the pairing. The energy gap created by this pairing could make the matter even more stable, resistant to small perturbations or cooling instabilities. Within a compact star, the transition from neutron matter to strange quark matter would begin deep in the core. As the density rises and deconfinement occurs up and down, quarks would dominate first. Then, through weak interactions, some of these quarks would transform into strange quarks, releasing neutrinos and allowing the system to settle into a lower energy configuration. If the strange phase is indeed more stable, the conversion could proceed outward, gradually replacing the star's interior with quark matter. The end result might be a strange star, a self-bound object made entirely of strange quark matter, with a thin crust of ordinary nuclei suspended above it by electric fields. The existence of such objects has not been confirmed, yet they fit within the theoretical framework of quantum chromodynamics and compact star physics. Their predicted properties differ subtly from those of neutron stars. Because strange matter is self-bound, a strange star could have a smaller radius for the same mass-producing slightly different gravitational signatures. It might also cool differently, radiating heat more efficiently through neutrino emission. Its surface would lack the conventional crustal structure of a neutron star, instead forming a smooth layer where quarks transition directly into vacuum. Observationally, such distinctions are difficult to detect, but they remain a focus of ongoing study. The concept of strange matter also extends beyond astrophysics. Some have proposed that small droplets of strange matter called strangelets could exist independently, perhaps formed in cosmic ray collisions or during the violent mergers of compact stars. These fragments, if stable, would carry fractional electric charge and extraordinary density. Detecting them would require sensitive instruments capable of distinguishing their unique energy signatures. So far, no confirmed detection has occurred. The absence of evidence neither proves nor disproves the hypothesis, since production and survival of strangelets under natural conditions remain uncertain. The idea that strange quark matter could represent the lowest energy state of matter has profound implications. It suggests that the universe might contain objects not yet identified existing silently among neutron stars and black holes. It also implies that the early universe during its first microseconds may have passed through a phase where strange matter dominated briefly before cooling into the matter we now observe. Some cosmological models propose that remnants of this phase could persist as dark, compact objects too dim to detect yet too dense to ignore. Each of these ideas depends on the same underlying principle, that the strong force under sufficient compression favors symmetry among quark flavors and stability through the presence of strangeness. Despite the elegance of the hypothesis, its verification remains beyond current reach. To confirm the existence of strange matter would require either the discovery of a compact star with unmistakable quark properties or the creation of stable strange matter in laboratory conditions. Both challenges lie at the edge of modern capability. Gravitational wave astronomy and precise pulsar timing offer the best hope for indirect detection. Mergers between massive compact stars compress matter to conditions that might reveal whether the transition to strange matter occurs. Subtle changes in the waveform or post-merger oscillations could carry the signature of quark conversion. Future instruments may have the sensitivity to distinguish these effects, narrowing the range of possible equations of state and bringing theory closer to confirmation. Until then, the strange quark matter hypothesis remains a bridge between nuclear physics and cosmology, a reminder that even in a universe governed by well-known forces, the ultimate form of matter may still be hidden. Within this concept lies the potential to connect the smallest scales of particle behavior with the largest structures of the cosmos, uniting the physics of quarks, stars, and space-time into a single narrative of stability and transformation. If strange matter exists, it represents not chaos but equilibrium, the quiet ground state beneath the layers of familiar matter, waiting only for the right conditions to reveal itself. Inside the most massive neutron stars, the matter at the center may begin to change in composition without altering the star's outward appearance. What appears from afar as a familiar neutron star could, in its deepest layers, conceal a core of deconfined quarks. This gradual internal transformation represents a quiet revolution in the nature of matter, a change that happens under the surface, invisible yet fundamental. The process begins when the pressure and density at the core exceed the threshold for deconfinement. Neutrons, which until this point behave as discrete entities, are forced so closely together that their boundaries dissolve. The quarks within them, up, down, and perhaps strange, merge into a continuous fluid. This transition is not explosive but smooth, governed by the balance between gravitational compression and quantum mechanical resistance. The boundary between the neutron mantle and the quark core is thought to be diffuse, a region where nuclear and quark matter coexist in a mixed phase. Here, droplets of quark matter may form and merge within a background of dense neutrons, gradually expanding as conditions favor the deconfined state. This coexistence is determined by minimizing the total energy of the system. In some models, the interface forms repeating structures of alternating phases, sometimes called a pastor phase, where matter organizes into sheets or rods depending on local pressure. Such structures, if they exist, would represent one of the strangest arrangements of matter in the cosmos, neither solid nor liquid but a hybrid of both. The presence of a quark core profoundly alters the star's internal dynamics. The density gradient steepens toward the center, while the equation of state softens slightly, allowing the star to compress further without immediate collapse. The core behaves as a near-perfect fluid with negligible viscosity and extraordinary thermal conductivity. Any heat generated in the inner layers spreads rapidly throughout the star, affecting its cooling rate. Quark matter, depending on its phase, may emit neutrinos more efficiently than neutron matter, allowing the star to lose energy faster in its early life. Observationally, this could explain why some young neutron stars cool more quickly than standard models predict, though the evidence remains inconclusive. The rotational behavior of a hybrid star also differs subtly from that of a purely neutron star. The presence of a quark core may alter the moment of inertia, changing how the star spins down over time as it radiates energy. Pulsar timing measurements sensitive to tiny changes in rotation could in principle reveal these differences, but the variations are minute fractions of a percent and easily masked by magnetic and environmental effects. Still, the possibility remains that among the known pulsars some may already contain quark cores without our knowing. As the fraction of quark matter increases, the transition zone moves outward. The star's overall radius contracts slightly, while its mass remains nearly constant. At a certain critical point, the core could encompass most of the interior, leaving only a thin outer shell of nuclear matter. In such a configuration, the star becomes what theorists call a hybrid star, part neutron, part quark, balanced in delicate equilibrium. The surface and magnetic field would remain those of a neutron star, but its heart would be entirely different. The presence of quark matter affects not only static properties, but also dynamic responses to stress. During starquakes, sudden rearrangements in the crust caused by magnetic or rotational forces, the energy transmitted inward might interact differently with a quark core. The rigidity of the outer layers contrasts sharply with the fluidity of the center, producing oscillations that could, in principle, emit distinct gravitational waves. Detecting such signals requires precision beyond current instruments, but as gravitational wave astronomy advances, it may one day become possible to probe the interiors of compact stars through their vibrational modes. The formation of a quark core depends critically on the star's mass and rotation rate. Rapidly spinning neutron stars experience centrifugal forces that slightly counteract gravity-reducing central pressure and delaying deconfinement. Over time, as they lose angular momentum through radiation, the central density increases. A pulsar that begins as a pure neutron star could, after millions of years of spin-down, develop a quark core naturally transforming quietly without any external sign. The transition would release energy, perhaps subtly altering the star's thermal or rotational evolution. The details of this process remain speculative but consistent with the equations of stellar structure. In a merging binary system where two neutron stars collide, the conditions for deconfinement are even more extreme. The combined mass and compression during the merger could trigger the formation of quark matter on a large scale. In simulations, this appears as a sudden softening of the equation of state, producing a characteristic feature in the gravitational wave signal. If such a signature were detected, it would be one of the first observational clues to the presence of quark matter in nature. So far, the data from observed mergers remain compatible with both ordinary neutron matter and hybrid models, leaving the question open. Theoretically, the growth of a quark core marks the beginning of a new regime of stellar equilibrium. The star is no longer supported solely by neutron degeneracy, but also by the pressure arising from quark kinetic energy and strong force interactions. This additional source of support allows it to remain stable at slightly higher masses. The boundary between neutron and quark regions defines a transition layer whose properties are complex and poorly understood. It must maintain continuity of pressure and chemical potential across two distinct forms of matter. Whether this layer is sharp or smooth depends on the details of quark interactions at intermediate densities, a problem that current models approach differently. Some predict a gradual crossover, others a first-order phase transition with a latent heat release. The physics of this layer could influence observable quantities such as the star's maximum mass, its oscillation frequencies, and its response to tidal forces. The existence of hybrid stars would provide a natural link between the confirmed reality of neutron stars and the theoretical domain of pure quark stars. They would occupy an intermediate region of the mass-radius diagram slightly smaller and more compact than neutron stars of the same mass. Their thermal evolution might also differ, with faster early cooling followed by a plateau as the quark core reaches equilibrium. These subtle differences are the focus of ongoing observational campaigns using X-ray telescopes and gravitational wave detectors. Yet despite decades of progress, no definitive evidence has yet confirmed the presence of quark cores. The signals are faint, the differences small, and the uncertainties large. The quark core remains a hidden structure concealed within the most extreme objects in the universe, inferred through equations and models rather than directly observed. Still, its possibility endures because it fits naturally within the framework of known physics. If neutron matter can exist and if quark deconfinement occurs at sufficient density, then the emergence of a quark core is not a speculative fantasy, but a likely consequence. The universe may already contain many such stars, quiet, compact, and indistinguishable from their neutron counterparts except in their deepest interiors. The challenge lies in detecting the faint echoes of their internal change, a task that requires both theory and observation to converge on the same hidden truth that beneath the crust of some neutron stars the world of quarks may already have begun, If a quark star exists, its internal structure would represent one of the most extreme and exotic configurations of matter in the cosmos. The entire object would be compact beyond comparison, smaller than a neutron star of similar mass, yet bound not only by gravity, but also by the intrinsic cohesion of quark matter itself. From the outside, such a star would appear unremarkable, a faint and compact point radiating weakly in X-rays. Its surface gravity would be immense, curving space so severely that light leaving it would be deeply redshifted. But beneath that surface lies an organization of matter, unlike anything else in the known universe, a stratified continuum where the familiar phases of atomic and nuclear matter give way to quarks moving in near freedom under the rule of the strong force. The outermost region of a quark star may still resemble that of a neutron star. A thin crust a few hundred meters thick could exist, where atomic nuclei remain intact. This crust would be supported by electrostatic forces that separate ordinary matter from the quark matter below. In most models, a strong electric field forms at the interface, preventing direct contact between the two states of matter. The result is a suspended crust of ions and electrons floating above a sea of deconfined quarks. Below this layer, the density rises rapidly. The transition zone between nuclear and quark matter acts as a boundary of immense energy, marking the point where neutrons disintegrate into their constituent quarks. Here up-down and strange quarks mingle in roughly equal proportions, creating a uniform fluid of extraordinary density. This inner region constitutes the main body of the star. It is thought to be color neutral overall, though locally filled with dynamic color fields that tie the quarks together. The matter behaves as a near-perfect fluid, meaning that it can flow without resistance and sustain global oscillations across its entire volume. The equation of state in this regime determines whether the star remains stable. If the quark matter is self-bound, the star's structure is defined not solely by gravity, but also by the internal pressure generated by the quark interactions themselves. Such an object could maintain equilibrium even with smaller radii than neutron stars of equal mass, a signature that may one day distinguish it through precise observations of compactness. In this state, the temperature gradients across the star are minimal, as the quark fluid conducts heat efficiently. The thermal energy stored during formation escapes primarily through neutrino emission, allowing the star to cool over time. In its youth, it may radiate strongly, but within millions of years it would become dark to most wavelengths, glowing faintly as a remnant of its original heat. The magnetic field inherited from its progenitor would thread through the entire structure, possibly reorganized by the presence of superconducting quark matter. The behavior of this field depends on the internal phase of the quark fluid. If color superconductivity occurs, magnetic flux lines may be confined to discrete vortices, creating a lattice that interacts with rotation. This could influence how the star spins down, potentially distinguishing it from neutron stars in its rotational evolution. The deeper one moves toward the center, the more extreme the conditions become. The pressure climbs to levels where the distinction between individual quark flavors fades and the matter approaches uniform composition. Theoretical studies describe this core as existing in the color-flavor-locked phase, a perfectly symmetric state, where up-down and strange quarks are paired across colors and flavors, forming a condensate that pervades the star. This state, if realized, would be remarkably stable, and could represent the ultimate form of matter before collapse into a black hole. In this phase, the matter behaves collectively, and the energy gap created by pairing suppresses some types of particle interactions. This affects both heat transport and neutrino emission, slowing the star's cooling after the first rapid phase. The entire structure from crust to core functions as a single coherent system. Vibrations in one region propagate through the whole body, with little damping giving rise to global oscillation modes that may in principle be detected through gravitational wave emissions during disturbances or collisions. The star's rotation further stabilizes the structure, distributing centrifugal force across the dense medium. At high spin rates, these forces flatten the poles slightly and influence the internal distribution of pressure. However, even at hundreds of revolutions per second, the quark matter's stiffness prevents large deformation. The surface remains nearly spherical, the entire star locked in a balance between gravity, strong interactions and rotation. The crust, if present, plays a minor role in the star's total mass, but an important role in its electromagnetic behavior. It may anchor magnetic fields, contribute to glitches in rotation, and emit bursts of radiation when stresses build and release. Beneath it, the electric field at the boundary can accelerate particles, possibly producing detectable emissions similar to those seen from pulsars. Yet the underlying quark matter surface remains smooth, lacking the conventional nuclear structure that defines neutron star crusts. Without such a structure, the star's outer boundary might act as a direct interface between the quark fluid and vacuum-emitting photons and leptons through processes unique to this environment. Such emission would be thermal and featureless, providing few spectral lines, making it difficult to distinguish observationally. Despite these challenges, the theoretical layering of a quark star remains one of the clearest frameworks in compact star physics. It divides naturally into three principal regions: the surface layer, possibly with a crust of normal matter, the outer quark envelope where deconfined quarks dominate but interactions remain complex, and the central core, potentially in a color superconducting or color flavor locked state. Each layer transitions smoothly into the next, creating a continuous profile of increasing density and pressure toward the center. The total radius may range between 8 and 10 kilometers for a star of roughly 1.5 solar masses, making it smaller and denser than any confirmed neutron star. The gravitational field near its surface would be so strong that even light struggles to escape, bending around the star in measurable ways. In such a place, the concept of solid, liquid, or gas loses meaning. Everything exists as one unified medium governed by quantum and relativistic laws. The structure of a quark star, while theoretical, encapsulates the culmination of matter's hierarchy. It begins with atoms, passes through nuclei, continues into neutron matter, and ends with quarks themselves, matter stripped to its most fundamental level, yet still forming macroscopic order. Whether such stars exist remains uncertain, but their predicted structure stands as one of the most striking intersections of quantum theory and astrophysics. They would be living demonstrations that the universe's smallest components can assemble into its most compact and enduring forms, bridging the scale from the subatomic to the stellar in a single continuous body. When a quark star forms, it is born in heat and pressure so intense that even the strong nuclear force bends to new configurations. The temperature in the first seconds after formation may reach hundreds of billions of degrees Celsius, briefly rivaling the conditions that existed in the early universe microseconds after the Big Bang. Yet this searing heat does not last. The star cools rapidly through processes governed by the weak interaction, emitting vast numbers of neutrinos that escape almost unhindered through the dense quark matter. This neutrino burst, invisible to most detectors, carries away nearly all of the thermal energy generated during the star's birth. In a matter of minutes, the internal temperature can drop by several orders of magnitude, stabilizing at tens of millions of degrees. After that, cooling proceeds, slowly driven by radiation and gradual neutrino emission from residual reactions inside the core. The mechanisms of cooling in a quark star differ subtly but importantly from those in a neutron star. In neutron matter, heat is carried primarily by degenerate electrons and by superfluid vortices in the neutron liquid. In quark matter, however, quarks themselves act as carriers of energy moving almost freely within the deconfined medium. Their collective motion allows heat to equalize rapidly across the interior, keeping temperature differences small. The surface may remain slightly cooler than the core, but overall the temperature gradient is shallow, and thermal equilibrium is reached quickly. Because of this, quark stars are expected to cool more uniformly and potentially faster in their early evolution, depending on the details of quark pairing and the degree of color superconductivity within. Neutrino emission dominates the cooling for the first million years of the star's life. Processes such as the direct Urca reaction, where quarks change flavor through weak interactions emitting neutrinos, can occur more readily in quark matter than in neutron matter, increasing the energy loss rate. The result is a rapid early decline in temperature followed by a slower prolonged phase as the star settles into a cooler state. The surface temperature during this later phase may fall below 1 million degrees, making the star nearly invisible in most wavelengths except soft X-rays. Over tens of millions of years, it becomes cold enough that even X-ray emission fades, leaving only faint traces detectable with highly sensitive instruments. The role of superconductivity within quark matter significantly alters these thermal pathways. If the quarks form pairs as expected in the color-flavor locked phase, the energy gap that separates occupied from unoccupied states suppresses certain reactions that produce neutrinos. This can slow cooling dramatically after the initial rapid phase, leading to a plateau in temperature that persists for longer than expected. In this case, the star retains its internal heat for extended periods, radiating it gradually through the thin crust or directly from the quark surface. Theoretical models predict a variety of cooling curves depending on the assumed internal composition, pairing mechanisms, and magnetic field strength. Observational data from neutron stars provide hints, but no definitive pattern that distinguishes pure neutron matter from quark matter. Some isolated neutron stars observed to be unusually cold for their age could in principle be hybrid, or quark stars, their enhanced neutrino emission accelerating energy loss. Others warmer than expected might exhibit superconducting phases that slow thermal evolution. For now, the data allow both possibilities. The outer layers of a quark star play a crucial role in how heat escapes. If a crust of ordinary nuclei is present, it acts as a thin insulating blanket, delaying the loss of energy. In stars without a crust where quark matter meets vacuum directly, radiation occurs from the bare surface itself. Such emission would consist mainly of electrons, positrons, and photons produced by electric fields at the boundary. This process, called pair emission, could dominate the luminosity of a young quark star for thousands of years, creating a distinctive signature, unlike the blackbody radiation of neutron stars. However, these emissions would weaken over time, fading as the surface cools and stabilizes. Deep within the interior, the temperature remains nearly uniform due to high conductivity. Heat transport is governed by quark scattering and the motion of collective excitations in the color superconducting fluid. The timescale for internal equilibration is measured in seconds, ensuring that the entire star behaves thermally as a single entity. Such efficiency means that any local heating, such as that produced by accretion or magnetic activity, would be redistributed rapidly across the core. The magnetic fields themselves influence cooling indirectly by guiding charged particles and affecting surface emission. In some models, magnetic stresses can trigger bursts or flares when the field reorganizes, injecting energy into the outer layers. These transient events may momentarily raise surface temperatures, though not enough to alter the long-term thermal evolution. As the star ages, its internal processes quieten. After about 1 million years, the neutrino luminosity falls below the photon luminosity, and surface radiation becomes the dominant means of energy loss. The star now behaves like a slowly cooling ember, its temperature declining logarithmically over cosmic time. Even after billions of years, it may retain a small residual warmth, protected by the immense density that prevents efficient heat diffusion. Eventually it approaches thermal equilibrium with its surroundings effectively dark to the universe, yet still existing as one of its densest remnants. The cooling of a quark star encapsulates the interaction between fundamental forces under extreme conditions. The weak interaction drives neutrino emission. The strong interaction determines the internal structure and transport properties. Electromagnetism governs surface radiation. Together they create a thermal evolution that unfolds over eons, revealing how energy dissipates when matter is reduced to its most basic components. Compared to neutron stars, quark stars might cool faster initially, but slower in the long term, their superconducting interiors preserving heat behind a barrier of quantum symmetry. These differences remain theoretical but testable in principle. Future observations of young compact stars, particularly those with known ages and luminosities, may allow scientists to compare their temperatures to predicted cooling curves. A deviation from the patterns expected for neutron matter could provide indirect evidence for quark matter within. In this way, the temperature of a distant star measured in faint X-rays becomes a clue to the behavior of quarks under the most extreme conditions imaginable. The story of thermal evolution is not merely about heat escaping into the cold of space, but about how fundamental interactions maintain balance even in the most compressed form of matter. A quark star cooling slowly in darkness embodies the persistence of energy in a universe where nothing remains still. Every degree it loses marks a quiet exchange between gravity and the quantum forces that oppose it, an equilibrium that continues long after light and motion have faded. The magnetic and rotational behavior of a quark star would express some of the most complex physical phenomena in the universe, linking the smallest quantum interactions to the largest astrophysical scales. Every known neutron star is a monument to angular momentum and magnetic field compression. And if quark stars exist, these properties would be even more extreme. When a massive progenitor collapses, conservation of angular momentum causes its core to spin at breathtaking speeds. A star, once rotating once every few days, becomes a remnant spinning hundreds of times per second. At the same time, the magnetic field that once extended across millions of kilometers is squeezed into a region only a few tens of kilometers wide. This compression amplifies the magnetic intensity to levels far beyond human comprehension, creating fields billions or even trillions of times stronger than any produced in laboratories. These conditions define magnetars and pulsars, the observed manifestations of neutron stars. For a quark star, the same mechanisms would apply but might evolve differently, as the internal state of matter changes how magnetism and rotation interact. Inside the quark matter core, the presence of color superconductivity could transform magnetic behavior entirely. In a color-flavor-locked phase, quarks pair in such a way that the color and electromagnetic forces intertwine, producing a modified version of electromagnetism, sometimes called rotated electromagnetism. This redefinition means that magnetic flux can penetrate the star only in quantized tubes, much as it does in a superconductor. These flux tubes would align with the rotation axis, creating a lattice of magnetic filaments threading the quark fluid. The motion of these tubes as the star spins down would determine how magnetic energy is dissipated over time. The coupling between rotation and magnetism thus becomes a delicate balance of quantum effects acting on a stellar scale. If the quark fluid is a perfect color superconductor, it may trap magnetic flux for extremely long periods, reducing the rate at which the field decays. In contrast, if the superconductivity is partial or unstable, magnetic energy could leak out more freely, potentially producing flares or bursts as field lines reconnect near the surface. These processes could explain transient events sometimes observed from highly magnetized neutron stars, though distinguishing between neutron and quark origins remains difficult. The rotation of a quark star also influences its internal structure. Rapid rotation flattens the poles slightly and redistributes mass toward the equator, changing the internal pressure profile. In neutron stars, superfluid neutrons form quantized vortices that align with the rotation axis, maintaining angular momentum. In quark stars, similar vortices may arise within the quark condensate, possibly linked to the magnetic flux tubes of the color superconducting phase. This intertwining of magnetic and rotational vortices could produce new kinds of instabilities, leading to subtle variations in spin. Observations of pulsar glitches, sudden increases in rotational frequency, have long been interpreted as movements of vortices in a superfluid interior. In a quark star, analogous events could occur through rearrangements of color vortices or magnetic structures within the quark fluid. Each rearrangement would release a burst of energy, detectable as a slight but measurable change in timing. Though such signals have been seen in neutron stars, their detailed behavior remains unexplained, leaving open the possibility that some originate in deeper quark-driven processes. The magnetic fields of quark stars could reach strengths exceeding 10 to the 15 Gauss, enough to alter atomic structure and dictate how radiation escapes from the surface. At these intensities, the vacuum itself behaves as a medium polarizing under the influence of the field. Photons of different polarizations travel at slightly different speeds, an effect known as vacuum birefringence. This phenomenon, if observed, could provide a direct measure of the field strength near the surface. Some recent X-ray observations have shown hints of such effects, though confirmation requires greater precision. If quark stars exist among these highly magnetized objects, their internal magnetic structure may differ in ways that subtly affect their emissions. The rotational stability of a quark star is also tied to its mass and equation of state. For a given mass, a quark star's smaller radius allows higher rotational speeds before centrifugal breakup. Some models predict that a quark star could spin stably at more than 1,000 revolutions per second, far faster than any known pulsar. However, if the interior is highly superconducting, the magnetic coupling between layers could impose limits, redistributing angular momentum and preventing excessive rotation. These interactions between magnetic fields and rotation define the long-term evolution of the star. As it emits radiation, it gradually loses rotational energy, spinning down over millions of years. The rate of slowdown depends on both the magnetic field strength and the moment of inertia, both of which could differ significantly for quark matter compared with neutron matter. Measuring these parameters accurately may one day allow astronomers to infer the presence of quark interiors indirectly. Another layer of complexity arises from the possibility of differential rotation. If the outer layers spin at slightly different speeds, then the core shear forces develop twisting magnetic field lines. In ordinary neutron stars, this process can generate magnetar flares or bursts of X-rays. In a quark star, the coupling between layers may be stronger due to color. Superconducting coherence reducing such activity or altering its pattern. The combination of immense density, rapid rotation, and superconducting matter thus creates an environment where quantum and relativistic effects merge seamlessly. Even the emission of gravitational waves may be influenced. Smaller symmetries in the magnetic or rotational structure can generate periodic ripples in space-time carrying away energy. For rapidly spinning quark stars, this could be a significant mechanism of energy loss, detectable with future gravitational wave observatories. Such signals would contain information about the star's internal rigidity, moment of inertia, and magnetic configuration, all fingerprints of its composition. The magnetism of a quark star also influences its surroundings. In binary systems where matter from a companion falls onto the star magnetic fields, channel the inflowing gas into narrow columns that strike the surface near the magnetic poles. The resulting hotspots emit X-rays in pulses synchronized with rotation. For a quark star, the surface properties could modify these emissions. The absence of a conventional crust means the infalling matter may interact directly with the quark surface, producing bursts of pair creation and photon emission. The resulting radiation could differ in spectrum and intensity from that of a neutron star, perhaps appearing smoother and more thermal. Over long timescales, magnetic braking continues to slow the star until it reaches a near-constant spin. The internal magnetic field decays gradually as energy dissipates through weak interactions. If the color superconducting phase is stable, this decay could take billions of years, leaving behind a fossil field frozen into the star's core. The rotation eventually becomes so slow that pulses cease, and the star fades into invisibility, a silent remnant sustained only by the balance of quantum forces. The study of magnetism and rotation in quark matter connects the smallest and largest scales of physical reality. Quark interactions determine the conductivity and magnetic response at the microscopic level, while these same properties govern the macroscopic stability of an object spanning tens of kilometers and weighing more than the Sun. This unity across scales exemplifies the power of physics to describe the universe through consistent laws. In a quark star, these laws converge. Quantum chromodynamics shapes the behavior of an entire celestial body, and general relativity frames its existence within curved space-time. Whether such stars exist remains unconfirmed, but their predicted magnetic and rotational signatures mark them as potential beacons of the extreme, a bridge between theory and observation, waiting to be recognized among the steady rhythms of the cosmic sky. When two compact stars spiral toward one another, the universe witnesses one of its most powerful and revealing events. These mergers, observed through gravitational waves and high-energy radiation, compress matter to conditions no experiment on Earth can reproduce. If quark matter exists inside neutron stars, or quark stars' collisions between such bodies may be the only moments when it becomes exposed to direct observation. Long before impact, the two stars orbit in a slow, gravitational dance, losing energy through the emission of ripples in space-time. Each orbit tightens the frequency of waves, rising steadily as the distance narrows. During these final seconds, tidal forces stretch and distort both stars, pulling matter from their surfaces and revealing clues to their internal stiffness. The response of each body to this strain encodes information about the equation of state, the relationship between pressure and density that defines its structure. If one or both stars contain quark matter, the deformation pattern changes, subtly softening the tidal response and altering the waveform detected on Earth. When the two stars finally touch, their collision releases more energy in a fraction of a second than the Sun emits in its entire lifetime. The impact crushes matter to densities exceeding those found in any stable neutron star, creating a single massive remnant. In some cases, this remnant collapses almost instantly into a black hole, but in others it survives briefly as a hypermassive star supported by rotation and internal pressure. During this transient stage, the internal temperature can exceed hundreds of billions of degrees, sufficient to dissolve even the strongest nuclear bonds. In these conditions, deconfinement is unavoidable. Quark matter forms within microseconds, perhaps throughout the entire remnant. This short-lived quark plasma radiates neutrinos, photons, and gravitational waves in a complex pattern that carries the signature of its composition. Simulations of such events suggest that if a quark core or pure quark matter region forms, it would alter the post-merger oscillations and affect how quickly the remnant cools and collapses. The gravitational waves would display a slightly lower frequency peak, and the electromagnetic afterglow could differ from that of purely neutron matter. These subtle effects are among the key observables scientists now search for in merger data, collected by detectors such as LIGO, Virgo, and CAGRA. In 2017, the first confirmed neutron-star merger produced a gravitational wave signal, followed by a kilonova, a burst of light powered by radioactive decay of heavy elements. That event confirmed that such collisions forge elements like gold and platinum, yet the internal matter remained hidden, as the signal did not extend into the high-frequency range where post-merger oscillations reside. Future detectors with greater sensitivity may reach those frequencies, potentially revealing whether quark matter appears during the final compression. The merging process also provides an environment for creating and possibly ejecting quark matter into space. In certain simulations, fragments of quark matter, small self-bound droplets sometimes called strangelets, could be thrown out at high velocity. If strange matter is stable, these fragments might persist as microscopic relics, traveling through space and colliding with interstellar dust or planetary atmospheres. Detecting such particles would be extraordinary evidence for quark matter, but none have yet been found. Even without ejection, mergers remain natural laboratories for testing the physics of extreme density. The violent mixing of matter produces conditions where hadronic and quark phases coexist and interact. Shock waves propagate through this hybrid medium, converting neutron matter into quark matter as they pass. The interplay between heating compression and phase transition determines whether the remnant stabilizes temporarily or collapses directly into a black hole. If it survives for more than a few milliseconds, magnetic fields amplified during the collision can generate relativistic jets, narrow beams of radiation that burst from the poles and produce short gamma-ray bursts. The composition of the jet material may also depend on whether quark matter forms at the core, influencing the energy and duration of the burst. Observations of these high-energy events thus provide indirect but powerful clues about the nature of matter at supranuclear density. The sequence of events in a merger is governed by general relativity and quantum chromodynamics acting together. Gravity shapes the orbit and collapse. The strong and weak forces dictate how matter behaves once compressed. In the first milliseconds after contact temperatures soar and densities double or triple relative to normal neutron star values, the matter becomes opaque to photons but transparent to neutrinos, which escape and carry information about the thermodynamic state. These neutrinos, if detected, would reveal whether quark deconfinement occurred, as quark matter produces a distinct spectrum. However, detecting neutrinos from extragalactic mergers remains far beyond current capabilities. In the absence of direct signals, scientists turn to models that combine hydrodynamics, nuclear physics, and general relativity to reconstruct what must happen. The inclusion of quark matter in these simulations often stabilizes the remnant slightly, allowing it to resist collapse for longer. The quark phase provides extra pressure at high density, delaying the formation of a black hole. When the transition occurs, latent heat is released, producing oscillations that radiate in gravitational waves. These waves fade within milliseconds, but could be recorded by next-generation detectors, providing an unmistakable fingerprint of the deconfinement process. Beyond their physical interest, mergers drive the chemical evolution of galaxies. The material ejected during the collision enriches the interstellar medium with heavy elements seeding future stars and planets. If quark matter forms even briefly, it could affect the quantity and type of elements produced, altering the pattern of nuclear synthesis. Thus, understanding whether quark stars exist is not only a question of fundamental physics, but also one of cosmic history. Each merger reshapes the universe's inventory of matter, bridging the microphysics of quarks with the astrophysics of galaxies. The magnetic fields generated in these collisions can also reach unprecedented strengths, twisting and reconnecting in patterns that power high-energy radiation. These fields, amplified by differential rotation, may interact with quark matter differently than with neutron matter, changing how energy is released in jets and flares. Some models predict that quark matter, being more conductive, could stabilize these fields, producing longer-lasting emissions. Observational confirmation of such effects would require correlating gravitational wave and electromagnetic data, a task that future multi-messenger astronomy will continue to refine. The merger of compact stars therefore represents both an end and a beginning. It marks the destruction of two ancient remnants and the possible birth of something entirely new, a transient quark object luminous for only moments, but revealing the deepest laws of nature. Whether that object collapses into a black hole or cools into a stable quark star depends on its mass rotation and the strength of the strong force itself. Each event offers a fleeting opportunity to glimpse matter at its limit, to see the universe write physics in light and gravity rather than equations. In that brief convergence of extremes, quark matter may emerge from theory into reality, its existence inscribed in the rhythm of space-time ripples spreading outward across the cosmos. The search for quark stars depends entirely on observation, yet the evidence they might leave is faint, ambiguous, and intertwined with phenomena already explained by neutron stars. Every potential clue must be traced through radiation, gravitational waves, or timing signals and interpreted within models that remain incomplete. The challenge is immense to distinguish one invisible compact object from another when both appear as points of light across astronomical distances. Still, nature provides tools for such a task. The light and motion of compact stars carry traces of their internal structure, encoded in how they emit, rotate, and deform under gravity. The effort to read those traces defines one of the most delicate frontiers of modern astrophysics. The first class of evidence comes from electromagnetic observation. Neutron stars that radiate as pulses reveal their rotation with astonishing regularity. By measuring the timing of their pulses and the small variations in that timing, astronomers can infer the star's size, moment of inertia, and sometimes its mass. These quantities depend on the equation of state of dense matter. A stiffer equation produces larger radii. A softer one implies more compact objects. Quark matter, being generally softer at extreme densities, would yield stars smaller for a given mass. Thus, unusually compact neutron stars, those with radii below about 10 kilometers for masses around twice that of the Sun, could indicate the presence of quark cores, or full quark stars. Measurements from X-ray telescopes, such as those observing thermal emission from isolated neutron stars, or from hotspots on pulsars, attempt to determine this radius precisely. Yet the uncertainties are large, and the overlap between neutron and quark models remains wide. No single observation can yet declare that quark matter exists, but each new dataset narrows the possibilities. The second class of clues lies in mass measurements. Binary systems where a neutron star orbits another star or compact object allow precise determination of mass through orbital dynamics. The discovery of neutron stars with masses exceeding 2 solar masses challenges many conventional equations of state, which predict collapse into black holes at lower thresholds. The existence of such heavy stars suggests either that nuclear matter is stiffer than expected, or that quark matter once formed provides additional support. Some theoretical models show that the introduction of a quark core can stabilize a star even at higher masses, allowing it to persist without collapsing. These high-mass pulsars therefore represent potential hybrid candidates, objects that quietly straddle the line between known and unknown states of matter. A third window comes from thermal evolution. As compact stars cool, their temperature follows predictable curves depending on their composition. Observing a star that cools faster or slower than expected could signal the presence of exotic matter within. For example, quark matter can enhance neutrino emission, causing rapid cooling in early life, while color superconductivity can later suppress it. Several neutron stars have been observed to cool unusually quickly, such as the one in the Cassiopeia, a supernova remnant, though alternative explanations involving superfluid transitions in neutron matter remain viable. The cooling behavior alone cannot confirm quark matter, but when combined with other indicators, it strengthens the case for deviation from standard nuclear physics. The advent of gravitational wave astronomy has opened an entirely new realm of evidence. When 2 neutron stars spiral together, the shape of the gravitational wave signal depends on how each star deforms under tidal forces. The degree of deformation reveals the internal stiffness, providing a direct probe of the equation of state. If quark matter softens the core, the stars would deform more easily, leaving a distinct imprint in the waveform. The merger detected in 2017, while groundbreaking, did not have sufficient resolution to determine this property precisely. Future detectors operating with greater sensitivity may detect multiple such events and extract detailed information about the tidal deformability of neutron stars. A pattern of unusually low stiffness across several mergers could indicate the influence of quark matter. Even the aftermath of such collisions provides clues. The light from kilonova explosions depends on how the remnant collapses and what material is ejected. If quark matter forms briefly, it could change the energy distribution, altering the color and brightness of the kilonova. Comparing observed light curves to models may one day reveal whether deconfinement plays a role in these cosmic fireworks. Another possible signal lies in the rotation of isolated pulsars. Sudden changes in rotation speed, known as glitches, are thought to arise from shifts within the star's interior. In a neutron star, they likely result from interactions between the crust and superfluid layers. In a quark star, they could arise from rearrangements of vortices within the color superconducting quark matter. Observing differences in glitch frequency or amplitude among pulsars might eventually hint at internal composition, though such interpretations remain uncertain. Quark stars could also display distinct magnetic field decay rates. If quark matter forms a perfect color superconductor, it would trap magnetic flux for far longer than ordinary neutron matter, producing unusually stable magnetic fields. Long-term monitoring of pulsars with persistent magnetic intensities might reveal such behavior. Similarly, their emission spectra, particularly in X-rays, could differ subtly due to the lack of a traditional crust or atmosphere. A bare quark surface might emit featureless thermal radiation, rather than the line-rich spectra seen from neutron stars with gaseous layers. Detecting such a smooth, black-body-like emission pattern could be a powerful clue though distinguishing it from other thermal sources remains challenging. Searches for smaller fragments of quark matter strangelets have also been conducted in cosmic rays and in particle accelerator experiments. These hypothetical particles would be tiny nuggets of strange quark matter stable over cosmic timescales. If detected, they would prove that quark matter can exist independently outside of stars. Instruments such as the Alpha Magnetic Spectrometer aboard the International Space Station continue to scan for unusual particle signatures, but so far none have been found. The absence of strangelets does not rule out quark stars, since the conditions for their ejection and survival are uncertain, but it leaves the question open. The interpretation of all these signals depends on detailed models linking microphysics to observables. Each measurement, mass radius, cooling rate, spin behavior, magnetic field, or waveform tests a different aspect of the same fundamental question: how matter behaves beyond nuclear density. The challenge is that multiple effects can mimic one another. A star with hyperons or other exotic baryons might appear similar to one with a quark core. Only by combining multiple lines of evidence can astrophysicists hope to isolate a consistent picture. This pursuit has accelerated as instruments improve. The NICER telescope aboard the International Space Station measures pulsar light curves to infer both mass and radius, simultaneously tightening constraints on possible equations of state. Upcoming observatories such as the Einstein Telescope and Cosmic Explorer promise to record hundreds of gravitational wave events, offering statistical power to identify trends that individual observations cannot. Step by step, the window of uncertainty narrows. What makes the search for quark stars unique is that it asks not merely for detection, but for discrimination between possibilities that differ only in their deepest layers. The observable universe provides few second chances for such precision. Each pulsar pulse, each merger, signal, each photon from a cooling remnant carries within it an encoded message from matter, compressed beyond the reach of laboratories. To read that message is to test the boundaries of physics itself. Whether the answer confirms quark matter or reinforces neutron matter, the outcome will clarify how nature arranges its densest forms. Until then, astronomers continue to listen to light, to gravity, to timing, to find somewhere among the steady rhythms of the cosmos the faint and final whisper of quark matter. At the center of every discussion about quark stars lies a single concept that determines their structure stability and even their existence, the equation of state. This equation, which links pressure, density, and energy within matter, serves as the bridge between microscopic physics and macroscopic observation. It dictates how matter responds when squeezed, how it supports weight against gravity, and how compact a star can become before collapsing into a black hole. For ordinary matter, the equation of state is well known, built from decades of experimental and theoretical research. For nuclear matter at moderate densities, it can be measured through collisions of atomic nuclei and the study of neutron-rich isotopes. But at the densities reached inside neutron stars, and especially within hypothetical quark stars, the equation of state enters a realm beyond direct experimentation. The behavior of matter under such compression depends on the strong nuclear force at conditions where it cannot be solved exactly from first principles. Quantum chromodynamics. The theory that describes this force becomes computationally intractable at high densities and low temperatures. As a result, physicists rely on approximate methods, models, and extrapolations that produce a range of possible answers rather than one. These models fall broadly into two families: those that extend nuclear physics upward in density, and those that begin with deconfined quark matter and extrapolate downward. Each approach carries uncertainties and assumptions. The nuclear-based models treat matter as interacting neutrons, protons, and exotic baryons. They are constrained by laboratory data, but may fail when particles overlap and lose their identity. The quark-based models assume deconfinement occurs and describe matter as a fluid of quarks interacting through simplified potentials. They capture the general features of quantum chromodynamics, but depend on parameters that are difficult to fix precisely. Between these approaches lies a transition region that is neither purely nuclear nor purely quark, where matter may exist as a mixture of both. This is the most uncertain part of the equation of state, and the one that most strongly affects the predicted properties of compact stars. The challenge is not only mathematical, but conceptual. The strong force binds quarks so tightly that separating them requires enormous energy, yet at the same time it confines them collectively in a way that resists description through conventional thermodynamics. Small changes in the assumptions about coupling strength, quark mass, or color. Superconducting gaps can shift the predicted pressure by large amounts. Consequently, two models built from the same underlying physics can yield stars that differ in radius by several kilometers or in maximum mass by an entire solar mass. Observations of heavy neutron stars therefore play a critical role in constraining these models. A confirmed mass above two solar masses immediately rules out many equations of state that are too soft to support such weight. The discovery of even heavier pulsars would further narrow the possibilities potentially pointing toward the presence of quark matter if nuclear matter alone cannot provide sufficient support. Yet while some observations push these limits, none have yet forced a definitive conclusion. The interplay between gravity and pressure remains finely balanced. The mathematical framework that connects the equation of state to observable properties is given by the Tolman-Oppenheimer-Volkoff equations, which describe hydrostatic equilibrium in general relativity. Solving them for a given equation of state yields the mass-radius relationship, the key diagnostic for distinguishing between different kinds of compact stars. For neutron stars, this curve rises steeply and then flattens near the maximum mass. For quark stars, it typically continues more gradually, allowing smaller radii for comparable masses. Observing both the mass and radius of a star with high precision therefore provides the clearest test, but such measurements are technically demanding. Instruments like NICER have begun to make progress, yet uncertainties in distance atmosphere composition and emission geometry still obscure the final answer. In addition to these macroscopic quantities, microscopic transport properties depend on the equation of state. Viscosity, conductivity, and heat capacity all influence how a star cools, spins, and radiates. The inclusion of exotic particles such as hyperons or meson condensates can dramatically soften the equation of state, lowering the maximum mass. To counteract this, models often include repulsive interactions at short range or transition to quark matter at high density, which restiffens the curve. The balance between these effects defines the possible landscape of compact objects, neutron stars at moderate masses, hybrid stars with quark cores at higher masses, and pure quark stars at the extreme. The uncertainty in the transition density, the point where nuclear matter becomes quark matter, remains one of the largest open parameters. Some models predict a smooth crossover, similar to how water gradually becomes vapor under certain conditions. Others propose a first-order phase transition, with a latent heat release, implying a discontinuous jump in density. Such a jump would produce a striking feature in the mass-radius diagram, creating a second branch of stable configurations sometimes called the twin star scenario. In this picture, two stars of similar mass but different radii could exist, one neutron-dominated and the other quark-dominated. Detecting both types would provide strong indirect evidence for deconfinement, yet observational precision has not yet reached the level needed to identify such pairs unambiguously. The equation of state also influences how compact stars merge and collapse. A stiffer equation produces more massive remnants and longer-lived post-merger signals, while a softer one leads to rapid black hole formation. Gravitational wave observations thus provide a new method to constrain the allowable pressure-density relations. The combination of these constraints with X-ray and radio data offers hope that the degeneracy between models will eventually break. Nonetheless, significant theoretical uncertainties remain. Lattice quantum chromodynamics, which simulates the strong interaction numerically, provides accurate results at high temperatures but fails at high densities because of a mathematical obstacle known as the sign problem. Alternative methods, perturbative expansions, Nambu-Joner-Lacenio models, bag models or functional renormalization group techniques each capture part of the physics, but none encompass it entirely. The field thus relies on comparison, a constant refinement of models against observation. Each improvement in measurement eliminates some equations of state and reshapes the boundaries of what remains possible. This iterative process mirrors the history of stellar astrophysics itself, in which observation and theory evolve together toward precision. The uncertainties in modelling do not weaken the concept of quark stars, but rather define the context in which their existence must be tested. The wide range of possible behaviours means that several scenarios remain viable. In some quark stars are stable and common, forming naturally from massive neutron stars. In others they are rare or non-existent with matter, collapsing directly into black holes beyond the neutron star limit. Distinguishing between these outcomes requires not just more data, but better understanding of the microphysics of dense matter. Laboratory experiments, though far from stellar conditions, continue to provide valuable constraints. Heavy ion collisions recreate small bursts of quark-gluon plasma, allowing scientists to measure how strongly quarks interact near the deconfinement threshold. These results, combined with astrophysical observations, help refine the equation of state from both ends of the density scale. In time, the convergence of terrestrial and cosmic experiments may close the gap of uncertainty. Until then, every parameter in the equation of state carries an implicit question mark, a reminder that deep inside the densest stars the behavior of matter remains one of the least understood domains of modern physics. The mystery of quark stars endures not because the theory lacks coherence, but because nature has placed the answer beyond the reach of direct measurement. Between the simplicity of equations and the complexity of stars lies a frontier defined by pressure density and the limits of human knowledge, a frontier still waiting to be resolved by the light and waves arriving from distant compact worlds. After decades of observation theory and simulation, the existence of quark stars remains one of astrophysics' most persistent open questions. The evidence, while intriguing, is circumstantial, drawn from the edges of known data from stars that appear too heavy, too compact, or too cool for their expected age. Every few years a new observation reignites discussion. A massive pulsar measured with unprecedented precision, an X-ray source with unusual thermal emission, or a gravitational wave event that challenges existing models. Each time the community weighs the same possibilities: anomalous neutron matter, exotic baryons, or deconfined quarks, and reaches no universal conclusion. The debate endures because the data fit more than one interpretation, and the physics of extreme density leaves wide room for uncertainty. One of the earliest clues came from pulsars with unexpectedly high masses, such as those near or exceeding 2 solar masses. These discoveries strain traditional nuclear equations of state, which predicted that stars this massive should collapse into black holes. To accommodate them, theorists proposed either stiffer nuclear forces at short range, or the inclusion of quark matter that could provide extra pressure. In such models, a quark core forms inside the star, making it more compact yet still stable. The possibility that these heavy pulsars might be hybrid stars, a bridge between neutron and quark matter, remains attractive, but definitive confirmation has not followed. Other potential evidence comes from measurements of radius and temperature. Observations by the NITR telescope have provided precise radius estimates for several pulsars, suggesting that some stars may be smaller than 10 kilometers across, while still weighing nearly twice the mass of the Sun. These dimensions are difficult to reconcile with purely hadronic matter, but consistent with quark or mixed cores. Yet the error bars remain large, and uncertainties in distance emission geometry and atmospheric composition blur the line between interpretation and speculation. Some models reproduce the data using conventional neutron matter by tuning interaction parameters. The ambiguity is a hallmark of the field. Every new dataset narrows the options but rarely excludes them all. Cooling behavior adds further complexity. Some young neutron stars, like the one in Cassiopeia, are cool faster than standard nuclear models predict. Quark matter could explain this through enhanced neutrino emission, particularly from direct Urca processes in deconfined quark matter. However, neutron superfluid transitions can produce similar effects. The same observation can therefore support opposite conclusions depending on the assumed microphysics. Even gravitational wave data, the newest frontier, has yet to resolve the question. The tidal deformability measured from the 2017 merger event suggested that neutron stars are somewhat softer than previously thought, possibly hinting at quark content, but the uncertainties were large enough to encompass all standard equations of state. Future detections with higher precision might reveal a sudden change in stiffness at high mass, or a distinct post-merger oscillation pattern, both potential signs of quark deconfinement. Until then, the debate continues between cautious optimism and skeptical restraint. Some of the most striking candidates for quark stars are X-ray sources that defy simple classification. Objects like RX J1856.5 32754 exhibit smooth, featureless thermal spectra without the expected absorption lines from a neutron star atmosphere. This could indicate a bare quark surface emitting as a near-perfect blackbody. Yet it could also reflect an unusually pure hydrogen atmosphere, or observational geometry. Similarly, compact remnants that show very small inferred radii, such as those in supernova remnants, sometimes match the predicted size of quark stars, but distance uncertainties and magnetic effects complicate the analysis. No single observation has yet provided the clarity required to declare discovery. Theoretical progress has been equally dynamic. Over the years, models of quark matter have evolved from simple bag models to sophisticated treatments, incorporating color superconductivity and finite temperature effects. These refinements show that quark matter can be either soft or stiff, depending on the chosen parameters, meaning that its inclusion does not automatically reduce a star's maximum mass. Some equations of state now predict stable hybrid or quark stars that can reach more than 2 solar masses aligning with observation. Others suggest that the transition to quark matter is delayed until densities too high to avoid collapse, implying that quark stars may never form naturally. The disagreement arises because the parameters of quantum chromodynamics under stellar conditions remain unknown. The coupling strength, strange quark mass and pairing gaps all influence the outcome, and each is uncertain within wide margins. Even the nature of the phase transition, smooth crossover or first order, remains debated. If the transition is sharp, stars might experience a sudden restructuring as the core converts to quark matter, releasing energy in bursts potentially observable as gamma-ray flares or gravitational wave spikes. If smooth, the change would be undetectable, blending seamlessly into the star's evolution. Both scenarios remain consistent with current knowledge. Observational campaigns have begun to test some of these predictions indirectly. For example, measurements of pulsar spin-down rates may hint at subtle changes in moment of inertia, over time possibly reflecting internal phase transitions. Likewise, population studies of neutron star masses suggest a bimodal distribution, with one group clustering near 1.5 solar masses and another near 2. Some researchers interpret this as evidence for two distinct families of compact stars, neutron and hybrid, separated by the deconfinement boundary. Others attribute it to selection effects or differences in binary evolution. The community remains divided not by lack of data, but by the complexity of interpretation. Beyond individual observations, debates also revolve around whether strange quark matter could be absolutely stable. If it were, even small fragments called strangeless might persist in cosmic rays. Extensive searches have yet to find any, but detection limits remain high. The absence of strangelays could mean that strange matter is unstable, or that conditions for their production are exceedingly rare. Without laboratory evidence, astrophysical observation remains the only viable path. The next generation of detectors may finally shift the balance. Upgraded gravitational wave observatories combined with improved X-ray timing missions will measure mass radius and deformability simultaneously for dozens of compact stars. With such data, it may become possible to determine whether a distinct transition in matter's stiffness occurs near twice nuclear density, a smoking gun for deconfinement. If confirmed, this would establish quark matter as a real astrophysical phase. If not, the mystery will deepen, but the bounds on possibility will tighten, bringing theory closer to certainty. The ongoing debate over quark stars illustrates how modern astrophysics advances not through sudden revelation, but through slow convergence of evidence. Each observation eliminates some options, constrains others, and refines understanding. The absence of definitive proof does not imply failure. It marks the frontier where measurement meets theory. Whether quark stars exist or not, their study has already transformed physics by forcing the union of quantum chromodynamics, relativity, and observational astronomy. It has expanded the concept of a star from a glowing sphere of gas to an object of pure quantum matter, governed by the strongest forces in nature. The discussions continue in journals, conferences, and simulations worldwide, with each new result reshaping the argument but never closing it. The persistence of uncertainty is a testament to the subtlety of nature's design. Somewhere in the silent catalogue of pulsars and compact remnants may lie the first true quark star, indistinguishable in light, but distinct in substance, waiting for the instruments and insight capable of recognizing what it is. Until that day, the debate remains open, an echo of curiosity reverberating across the universe, inviting each new generation of scientists to look deeper into the densest hearts of dying stars, and ask again what matter becomes when nothing can compress it further. At the present frontier of astrophysics, the question of quark stars embodies both the power and the limitation of human inquiry. It gathers within one idea the deepest principles of quantum mechanics, the complexity of nuclear physics, and the immensity of relativistic gravity. Each framework explains a different layer of reality, yet inside a compact star they coexist interlocked and inseparable. A quark star, if it exists, is the natural meeting point of all these domains, a single object where the smallest known particles collectively shape one of the largest and most enduring forms of matter in the universe. The pursuit of such an object reveals not only the structure of stars but also the reach of the laws that govern everything else. At its core, this search begins with the simple question: how far can matter be compressed before it ceases to be what we know? The answer lies beyond the threshold of neutron degeneracy, where the pressure from quantum exclusion is overwhelmed by gravity's insistence. Beyond that threshold, the neutrons themselves begin to dissolve, and a matter crosses from the nuclear to the subnuclear regime. What emerges may not be a different material so much as a different definition of existence. In this new regime, the concept of individuality among particles fades, replaced by collective behavior under the strong force. The quarks move in a fluid sea of gluons bound not into discrete nucleons, but into continuous fields of energy. This deconfined matter, though theoretical, represents a natural extension of known physics. Its stability and form depend on the same equations that describe protons and neutrons, simply extended to conditions never tested in nature, except perhaps within these collapsed stars. The line between neutron star and quark star may therefore be less a boundary than a continuum, a gradual transformation that occurs silently deep within massive remnants. To detect such a transformation requires observing what cannot be seen directly, the behavior of gravity, light and matter at the surface and beyond. The curvature of space-time around these objects encodes information about their density and structure, bending the light that leaves them and altering the rhythm of their pulses. Each observation of a pulse's rotation or an X-ray spectrum becomes a fragment of a larger picture, a map of the unseen interior built from signals that have crossed the cosmos. Even now, as telescopes measure the faint light from stars thousands of light years away, the inner composition of these stars remains beyond reach. The universe allows observation only from the outside. Yet this limitation has not deterred progress. Through careful inference, through the combination of theory and measurement, scientists have reconstructed the properties of stars, galaxies, and even the early universe itself. In the same way, the existence of quark stars may one day be inferred not through a direct image but through patterns repeated across multiple lines of evidence. A small difference in mass-radius relations, a particular cooling curve or a consistent tidal signature in gravitational waves could finally confirm what equations have long suggested, that matter can exist in a state more fundamental than the neutron. The unseen frontier of matter is not a distant region of space, but a scale of density and energy beyond current access. It is a domain where the strong force governs structure instead of the electromagnetic, where the familiar chemical order dissolves into pure quantum interaction. Within it, the symmetry of nature becomes evident. The same laws that bind quarks within a nucleus also determine the equilibrium of a star 20 kilometers across. This unity of scale reflects one of the universe's most elegant qualities, that its extremes mirror its foundations. The smallest and largest forms of matter obey the same principles, simply expressed under different pressures and magnitudes. The recognition of this symmetry has driven theoretical physics for generations. Each discovery, from the first identification of neutrons to the detection of gravitational waves, has expanded the framework in which nature can be described. The hypothetical quark star continues that expansion, pressing the theory of quantum chromodynamics to astrophysical limits. Its study forces scientists to confront unsolved problems: how confinement breaks, how color superconductivity behaves, and whether strange quark matter can be stable. These are not only technical questions, but philosophical ones about completeness and comprehension. To know whether quark stars exist is to know whether the equations of the strong force fully describe matter, or whether another layer of structure remains hidden. The frontier is invisible, but its edges are sharp. Observational technology continues to advance toward it. Instruments now measure pulses with microsecond accuracy, gravitational waves with fractions of a wavelength, and X-rays from the farthest remnants of supernovae. Each improvement brings theory closer to testable reality. The future may hold missions designed specifically to probe compact stars across multiple wavelengths, combining electromagnetic, gravitational, and neutrino signals. In such multi-messenger observations, patterns could emerge that no single channel reveals. The discovery of a sudden softening in stellar matter, a characteristic vibration after a merger, or an unusually compact yet stable remnant would each provide a decisive clue. In time, these details may accumulate into certainty. When that happens, the confirmation or refutation of quark stars will reshape the understanding of cosmic evolution. If they exist, they represent an intermediate destiny for massive stars bridging neutron stars and black holes. They would mark a new equilibrium between collapse and stability, proving that nature allows one more configuration of matter before gravity wins completely. If they do not exist, their absence would still clarify the boundary of the possible, confirming that neutron matter is indeed the final state before the event horizon. Either outcome completes the story that began with the first collapsing stars billions of years ago, when fusion ceased and gravity took command. The search for quark stars also holds a symbolic significance. It reflects the human drive to understand not only what can be seen, but what must exist for the universe to make sense. The concept unites the smallest building blocks of matter with the largest structures of the cosmos in a single narrative of transformation. In this sense, the frontier is as much intellectual as physical. It challenges the boundaries of observation theory and imagination at once. Each equation written for the strong force, each simulation of stellar collapse, each detection of a distant pulse represents a step toward understanding the balance between confinement and freedom, between the finite and the absolute. Quark stars, whether real or only theoretical, serve as reminders that knowledge advances by approaching what cannot yet be proven, by pressing against uncertainty until it yields coherence. They embody the persistence of curiosity, the quiet insistence that even in a universe ruled by gravity and decay, new forms of order may still emerge. At the unseen frontier of matter, science approaches its own horizon, where questions about density and structure turn into questions about comprehension itself. Beyond that line lies the domain of speculation, but just before it lies the realm of discovery. It is here in the narrow space between what can be measured and what can only be inferred that the idea of quark stars continues to endure, unseen, unconfirmed, yet entirely possible, suspended at the meeting point of physics imagination and the endless density of the unknown.